Good day. On this video, we will discuss the Doppler effect. Let me show you another video.
Alright, this is how the song really goes, okay?
Now let's discuss through this little app, this simulation, what's going on. I'm going to add, what we have here is a source of sound. Right, I'm going to actually decrease the frequency a little bit, and then I am going to draw. I'm adding an observer here, you see, and then this is the source of sound. As you can see, nothing is moving. The wavelength of the sound can be measured from peak to peak or valley to valley. Now look what happens as the source starts moving towards the listener. You can see how the frequency increases because the wavelength decreases. As the observer moves, the wavelengths become the wavelength becomes shorter, and that means the frequency increases. As if I do the opposite, it's hard to do this consistently. But look at the wavelength. Look at the wavelength in front is shorter and behind is big. So what the observer perceives is a longer wavelength. And that means low frequency. So this is the first case we observed. You get Doppler effect when a source of sound moves with respect to an observer. The other possibility is that the source of sound doesn't move, but what moves is the listener or the observer. Let's look at the perceived sound down here. As I move, you see the frequency appears to increase. It's not because of the sound, the source sound moved, it's because the observer moved. And if I do the opposite, if I move away from the source, you see the wavelength decreases. Look, let's do the extreme case. What will be the wavelength decreases, the frequency decreases? What will be the frequency if the source stays where it is without moving and the observer moves almost at the same speed as the crest itself? This is very hard to do, but you will see. You probably can. Well, I cannot do it with my mouse. It's very hard. But if I try, well, the amplitude remained nearly constant, meaning the frequency became zero. If I'm, let's just remember something very quickly. If I'm in a car and there's somebody here and I throw a ball at 10 meters per second, right? If I'm not moving and this person is not moving, the person will catch the ball at 10 meters per second. Now, if the car is moving at 5 meters per second towards the person, the perceived speed of the ball when it reaches will be 15 meters per second. If I'm moving away, the perceived speed will be 5 meters per second. The same thing happens if it's the person moving. If the person moves towards the right at 8 meters per second, then the ball reaches him at 2 meters per second. If the person is moving against the car, right? Let's say the car is not moving, just the 10 meters per second on the ball, but the person moves against the ball at 10 meters per second, then he will perceive the ball reaching him at 20 meters per second. This is called relative velocity, and is related to Galilean relativity. Okay, with that in mind, let's see what happens with sound. When what we saw is that the source of sound is here, right? So, and then we said that the source can be moving, the receiver can, the perceiver, the listener and source can be moving as well, left and right. Let's first see what happens when the source moves. When the source moves, the source starts here, emits sound, right? So let's say after a certain time, the whatever sound was emitted from this position is here, right? This is difficult for me to draw circles. I'll try again. Okay, so it's there. But then at this in this time, it took the wave to arrive there, because the source is moving. The source arrived here, and then here comes the next sound. All right. So what is the wavelength? The wavelength of the sound is, well, from here to here. This is the wavelength in front of the source. You see, this distance here, remember speed is distance over time. So any distance is speed times time. So this distance is the speed of sound times, let's say, 1 period. Well, here, that looks like an S. It's a V, is the speed of sound times the period. Let's say, and then from here to here, this is the speed of the source times the period. So you see how the wavelength in front is this big radius Vt minus this little chunk Vst, right? Or V minus the speed of sound, the speed of the source, the period, or speed of sound, speed of the source over the frequency. This is the wavelength in front. And if I want the wavelength behind, let's say the wavelength behind will be all this from here to here. This is the distance between one wavefront and the next one. Well, all you have to do is put here a negative, a plus, because it will be the big radius Vt plus this chunk Vst. So that's the wavelength. That's how the wavelength changes in front of or behind the source, where this f is the frequency that the source is emitting. Okay, so S source is S, listener is L. So what frequency does the listener perceive? Remember that velocity is lambda f, so any frequency is speed of sound over lambda. So the frequency the listener receives is the speed of sound over the wavelength the listener receives. But that's this one. Either front, or depends where you are. Is the listener in front of the source? Is the listener behind the source? So instead of lambda listener, I'm going to put all this. So V plus minus the speed of source over the frequency of the source. This is the frequency the listener detects when the source is moving. Now, what if the listener is moving? If the listener moves, this is still true. The frequency the listener hears is the speed of sound over the wavelength the listener perceives. Now, if the listener moves, you are in this scenario. It's the same thing. The pitcher is sending you balls at 10 meters per second, but now the observer or the catcher is moving towards the balls. So the speed of the ball is the perceived speed of the ball. The relative velocity is the speed of the ball plus or minus the speed of the catcher, or in this case, the listener. Well, see, the same thing happens here. if the listener moves, the frequency changes because the speed of sound changed. The relative speed of sound is different. So it's going to be the speed of sound plus or minus the speed of the source. And then here you have whatever wavelength, which is constant in this case, right? In this case, the source is not moving, it's the listener moving, either towards the source or away from the source. So the wavelength the listener receives is constant. And this is how the frequency will change if the listener is moving. Well, I'm going to combine these two equations. I'm going to put in the numerator what happens if the listener moves, which is the same thing here, and I'm going to put what happens if the source moves, which is what we put on the other one. Oh, there's a mistake here. This is the listener. That's what I put here, the listener. This is the frequency changes because the listener is moving. So here, excuse me, let's put it here. And then you have, and this is the general expression for Doppler effect in the case the listener moves or the source moves or both move. The plus minus, how do we deal with the plus minus? Let me show you. Remember, the L means listener, the S means source. So how do you do a problem? This is the general expression. Let's do a quick example. Let's say you have a car moving to the right. This is the one generating sound. It's a police car. So there's a siren. There's a siren. So the source is moving at 10 meters per second to the right. And here you have a listener that is not moving. The speed of the listener is 0. How do we determine the frequency the listener will detect if the car is moving at 10 meters per second? Let's say the frequency of the car is 3000 hertz, the siren. So what you will do, V and V, this is the speed of sound. So let's just use 343. 343. The listener is not moving, so 0, and the source is moving at 10 meters. Everything is in meters per second. So now what do you do with the plus minus here and here? Well, there is a very simple rule that I can show you. What you do is you draw an arrow from the listener towards the source. And this determines your positive direction. So with respect to this vector, this reference, always for listener to source, always listener to source. So with respect to this reference, you see VL doesn't matter because it's not moving, but VS is negative. So you put a negative and then you get your answer. Oh, sorry, times the frequency of the source, the 3000, and you get your answer. 3090 hertz. You see it's higher. This is what we expected. You're moving towards is going to be higher pitch. What if, we'll do it again. Let's do it again, but now let's say the listener is moving towards the right at 5 meters per second, but the source is moving towards the left at 10 meters per second, but now towards the left. So we do this again. 343, 343. The frequency is 3000. And now the listener is moving at 5, the source is moving at 10. Once again, we draw reference listener towards the source. This is our positive. So with respect to this positive reference, the listener is moving against the reference and the source is moving with the reference, so we put a plus. If you do the calculations, you get 2802.5 hertz, so less than you expected, less than the original 3000, right? We'll do more problems involving this in class.